So I'm going to throw in some terms and some little rules here that are going to help to guide you through the next little bit of this course. There's a lot to pick up, but it is quite repetitive once you get going, so it should be okay. We have a scenario kind of like the get started thing here, where we've got our y-axis and our x-axis. We have a line drawn out from the center. We call this the radius because it's anchored here and going out here, and I could move it. I could even turn it around to make it a whole circle. So the radius is just the distance from the middle here of the graph out to where the point is. Now the point itself is x and y. Every point is x and y. But what's unique about this one is that we're actually drawing a right angle triangle and saying that y is the height here and x is the length of the base of the triangle. So we're sort of superimposing a triangle onto a graph. We can use all the rules of triangles to solve it in the context of a graph. So what they want us to do here is to write an expression for r in terms of x and y. Well, that's what we did in the last one, because we have that x squared plus y squared, this side plus this side equals that side squared. So if I want to make an expression for r, I just have to make it the square root of x squared plus y squared. Now that's a handy formula that you can use for any right angle triangle, and when we're dealing with a scenario in standard position, which means that you're going up from the x-axis, if this were a radial arm and you were picking it up, you're going up from the x-axis in a counterclockwise way, and you're hitting somewhere along the line point P. So you'll always be able to draw a right angle triangle to the x-axis and break it down into the points x and y, because that's how high it's going to be off the x-axis is your y value, and how far out it's going to be is your x value. All right, the next thing they want is the value of theta in terms of x and y. Now I skipped this in the get started. Apologies for that. Hopefully you can follow along. Theta is the angle, and what you may remember is SOHCAHTOA. So to use SOHCAHTOA in this situation, we recognize that this is the hypotenuse, this is the opposite, and this is the adjacent side. Now the nice thing about this is they never change, because this is always the angle we're interested in relative to x, never relative to y, not on this side, here. That's standard position, always relative to the x-axis. So that's always going to be my opposite. Y will always be the opposite. X will always be the adjacent, and the radius will always be the hypotenuse. So these things kind of stay the same, and it's kind of nice because when we did trig before, we always had to figure it out. So if we want to figure out theta, then you could try to remember, SOHCAHTOA, and remember that that gives us the formulas. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tan is opposite over adjacent. Well, I have opposite and adjacent. I don't have hypotenuse, I have the coordinate points. So I'm going to pick tan as the one to solve here, and it'll always be that way when you have the x and the y coordinates. So I can look at my formula. I want the angle, so I'm going to go tan second function of opposite over adjacent, which is y over x. So my y coordinate over my x coordinate will give me theta. So now I have an expression that lets me figure out theta. But what if I wanted the x coordinate and I had r? So the next thing they want us to know is, say they give us the length of r and they want the x coordinate. Well, now they have the hypotenuse, we have the angle, and we want the adjacent. So hypotenuse and adjacent makes me talk about cosine. Now, I'm solving for the adjacent, so I'm going to go cosine the angle times hypotenuse. So x, being the adjacent, will be equal to cos of the angle times the radius, which is the hypotenuse. And the last thing that they want us to know is, how do you find the y-coordinate if you have the radius and theta? So we're looking for opposite now. If we want the y-coordinate, which is opposite, and we have the hypotenuse, we're going to look for the ratio that uses opposite and hypotenuse, and that is sine. So I can say that y is going to be equal to sine theta, and again, it's opposite, so I cover up opposite. It tells me I'm going to go sine theta times the hypotenuse, which is the radius. So my hypotenuse equals my radius. I plug it in where the hypotenuse would go. Now I have 4 nice tidy formulas for getting this information out of this diagram. There's one final, I guess, just arrangement that we can do here, and that is to use, we can just write this out. And this is on the bottom of page 427 in your textbook. They just use these identities to show you how, if you have the radius and theta, you can just figure out the coordinate point without constructing the triangle or anything like that. You can just go x is cos theta times r. So we just write that in, cos theta times r. And y is sine theta times r. So they just tell you that that's how you could get those points without having to worry about setting up the triangle, because the triangle in standard position will always be up in a counterclockwise direction from the x-axis. This will always be the angle, never this one. And so you can always use that y is the opposite, x is the adjacent. You can set your stuff up like that and solve it.